Good afternoon and welcome again to Environmental Geology. This is Lecture 4 and our main focus today will be on earthquakes. And specifically today we're going to do a little more detail about earthquakes, some of the actual vibrational characteristics, and look at some of the other things. So the main theme will be quakes, seismology, and tsunamis, and you'll need to focus on Chapter 3 of Abbott in your textbook. Oops. All right, seismology. I've got an interesting little picture here in the top left-hand corner we're going to look at more closely later on. And you see if you can, there's a little yellow arrow pointing to an individual up in the water here. We're going to see what's going on with this particular person. So there's sometimes some pretty interesting things about earthquakes, but sometimes there's some very scary things about earthquakes. So we're going to focus on seismology today. Seismology is the study of wave vibration, or more generically, the study of earthquakes and those waves that go through the earth. So what is an earthquake? How could we real simply define an earthquake? And a really simple definition of an earthquake is it's a vibration of some sort. The ground shakes, the earth vibrates. That one of the main causes for this will be rocks that are under stress that break and become offset. We refer to this as a fault, and there's different kinds of faults. We'll look at some of these faults a little more closely towards the end of the lecture today. So in this, rock will become offset, some type of displacement of several inches or several feet, and the energy that was built up at the time of this break on the rock, the faulting, is dissipated into the earth. So again, the study of earthquakes will be seismology. Now we'll have instruments out there that can record earthquakes. And so we'll refer to this kind of a category of seismographs. They're an instrument used to measure quake vibration. And we'll take a look at a couple examples of some of the kinds of instruments that we use to do this. I'll give you a little time to make sure you get caught up on that note there. Now, where do we have most of these earthquakes taking place? In the last lecture, we looked at the concept of plate tectonics, the theory of plate tectonics, that the outer, brittle portion of the earth is moving, whether they're colliding head-on or being pulled apart or sliding sideways past another. So it's the main earthquake activity that we see and record on the planet takes place at these plate boundary types. For example, right here in the central left, along a rift system where the crust is splitting and pulling apart, the forces involved are taking these rocks and through tension, pulling them apart, overriding the strength of the rock, and they break. And so that pent-up energy is then given off as a type of vibration, an earthquake right here. Where the plates are hitting head-on, a convergent type of boundary, we get some of our strongest and greatest types of earthquakes. The biggest ones occur where the subduction zones are, where the plate will subduct back down into the mantle. And rocks under a great deal of stress will, of course, give us our largest events. This third example we looked at in the last lecture are transform faults. That's where the plates slide sideways past one another like the San Andreas Fault. And again, the rocks will be under stress and they will eventually break. And the energy given off is an earthquake. So you have to think about what's going on. As these plates move around, the rocks are put under stress. And rocks have different strengths to them. Some rocks are weak, some rocks are strong. So if you can have this stress build up and build up and build up, the response will be some form of strain that's going to place. The rocks will bend or fold or recrystallize. But once that stress exceeds the strength of the rock breaks in a brittle manner. And that energy that was built up and pent off then, of course, is dissipated into the earth. And that's what we feel as a vibration as an earthquake. This three-dimensional block diagram kind of shows us where faulting and what faulting would look like at the surface of the earth and inside the earth. Now the top part of this diagram would be like the map, the surface of the Earth. And this line that runs across the top is where the fault, the actual displacement, can be seen. It's referred to as the fault trace. And on geologic maps, we'll see a lot of these fault traces shown as extra thick, solid lines on the map. And right here, they're showing you where the actual rupture, the actual physical displacement took place in a much thicker line across here. And they're projecting it across these other areas, even though it was not ruptured at that point. So the actual break, the actual fracture, is shown on the surface of the Earth as a line. But inside the Earth, it's more of a planar to curviplanar-like structure. And they show that in the stippled area, kind of inside of this, the rupture area, the actual break where it takes place. Now we learned last lecture that we put a dot on the map physically and vertically above this rupture area where the earthquake took place, and we call it the epicenter. Well, the epicenter is shown as a dot here, but it only represents maybe displacement that would take place at depth right down here where we define the actual break, called the hypocenter. But in reality, this whole stippled area was actually broken and shifted. It had offset to it, had some type of slip. And all that energy that was built up is released when that breaks and fractures. And this energy is given off from that whole surface area in different types of waveforms. And we'll be looking at those waveforms in just a moment. So if we were to try to say, well, how come we don't have dots over here above all this area? We should. There should be a bunch of epicentral dots all over the place and dots all over the whole hypocenter. So in this three-dimensional block diagram, the actual hypocenter is that whole stippled area. And depending upon what rocks are involved and how much energy involved, that could be a small zone. Notice there's no units on here in terms of feet or meters. There's kind of unitless. But it could be a much larger area. And we're going to see that later on we evaluate how much energy is given off at that point. Understanding how big this surface area is plays a role in that part of it. And we're also going to see later on today, how do we record these vibrations that are given off when this rock ruptures? We'll take a look at some of that. Now here's a nice surface expression of a surface trace. You can see in this kind of freshly contoured or plowed field, you can see the rows before the plants have come up, and all of a sudden they've been dramatically offset right in that spot. That's the fault trace. So right at that surface and below it, there's been a fracture of some sort, and it appears to be about a foot or so of displacement or offset. And so this would be the epicentral position and also the hypocenter as well. All right, a seismograph or a seismometer is an instrument we use to record the earthquake vibration. A seismograph or seismometer is a type of instrument that measures that. There's lots of different styles and makeup of types of seismographs that are out there. Some are simply mechanical, some are electronic, some are digital, some are optical. The one shown here is kind of a real simple diagram where the bottom concrete base or plate is attached to the earth. And if the earth vibrates or moves, then that whole plate shakes and vibrates too. Now with the arrows, they're showing this just moving in a particular direction, back and forth and back and forth. Also attached to that base is a cylindrical drum with a piece of paper wrapped around it. And suspended above that, you have kind of a weight, they say, with a little pen attached to it. Could be an ink pen, doesn't matter what kind of pen, an optical pen, a digital pen. That stays stationary because it's suspended on a wire of some sort. Whereas it's the base that moves. So when the ground shakes, this whole thing moves back and forth and records a little wiggly line on there. In the top right-hand corner of the diagram, you can see a schematic of what we call a geophone, an earth phone that measures vibration, particularly in the oil industry or mining industry, where we will detonate a charge on purpose or vibrate the ground on purpose, send signals into the ground, and then have those signals reflect or refract back to the surface, and we measure that. Now, inside this thing, again, we have the base. The base of the geophone is attached to the solid ground, and there's kind of a cylindrical cover to it. And then inside that, you'll see another small cylinder like a hollowed out tin can suspended on a little spring. Right up here, there's a little spring, and that's suspended. Inside of that suspended spring and attached to the base and the bottom is a magnet. Okay, a magnet. And around that hollowed out can-like cylinder are wires that are wrapped around it. So if you know in physics, if you move a magnet up and down or through and back and forth across kind of a coil that's got wires with electricity going through them, you'll call it a voltage flux to take place, and you can measure the intensity of the movement. So when the ground moves, the magnet moves, that whole thing shuffles up and down, but that little can does not. It behaves just like the suspended weight over here. And so it will measure a certain amount of up and down motion. So this one happens to show a way in which you can measure up and down motion. There can be sideways motion like they're shown here. So in space, we want to have movement up and down, sideways along a north-south direction, and sideways along the ground in an east-west direction. So usually there's 3 different styles of seismographs that are out there, okay, recording the earthquakes. And some have real strong tensional springs on them. Some are weaker, depending upon what we're trying to record. A real gentle vibration, you better have something that moves real easy. But if it's a big earthquake, and you know you're near big earthquake activity, you want a more stronger spring system, such that when the ground vibrates, you don't have the needle going off, off the end or breaking because of the amount of force that's involved. So there's different styles of, seismographs of all different shapes and sizes, and they keep improving these on an annual basis. Now, if I were to take this strip of paper off this drum with the recording of the little wiggly lines, that's referred to as a seismogram, like a telegram. Okay, a seismogram is that piece of paper that shows those vibrational patterns. And we look at these seismograms, we see that many of them can be very complex and kind of complicated to unravel because of the vibrational styles, but some can be fairly straightforward and simple, like this one shown here, where we get in this left area on the diagram, the first arrival, the ground begins to vibrate up or down, a needle begins to move. That's the arrival of the first wave. The first wave, another word for first is primary. So we say that's a P wave. P can be for primary. P happens to stand for something else too. Push, pull. We'll get to that in a little bit. And then some time passes and you get another arrival of another wave. In this case, we'll have the S wave. Secondary, because it gets there second, so to speak. But S stands for another thing just as well. So when you look at this, you can see that there's pulses and packages of first arrival of vibrations and second packages and so on. And one could argue, well, this is the first arrival, that's a second, and this is a third. Depends on how complex the patterns get. But they only can get so high. You notice this is kind of a graph paper on there. We can give a unit to that graph. We could get out an instrument and measure how high the amplitude is. I'll come back to that later and what that means. So a seismogram is the record on a piece of paper of this actual vibration. One of the main places in the United States for seismographs to try to pick up and have information sent to them from all over the country and the world as well is in Golden, Colorado. The National Earthquake Center for the United States is in Golden, Colorado, kind of in the central part of the country. And there are seismograph stations from all over tied to that. Here in Kansas at Cedar Bluff Reservoir, several years back they installed a seismograph station, and the data picked up there is sent to Golden and recorded, and they keep records of all this stuff and compare what those seismograms looks like, and they evaluate them in terms of how much energy was actually dissipated by this earthquake. We want to know that. And again, I'll explain why we want to know that. So again, seismograms are simply a record of the vibration. They usually have a nice initial P wave, a primary wave, then a secondary wave, and then some other kinds of wave styles that take on a different kind of amplitude and frequency after that, stylistically. And so as we see here in just a bit, we're going to be able to talk about vibrations that are going through the body of the Earth as opposed to new types of vibrations created as those body waves hit the surface of the Earth and make new waves, surface waves. So these, they can have one here labeled L, I'll explain what an L wave is in just a moment. It's a love wave of all things, and named after a geophysicist. And so there's different styles of new vibrations that develop. Now, this just happens to be something I threw in, kind of an interesting type of seismogram that was recorded at Columbia University. And it's a record of when the World Trade Center got hit on 9/11. And if you look along the lines here, you can see that as we start at the top left on the red line, as you move from left to right, there's a little bit of vibration going on here. That's background noise. It could be traffic, wind, whatever, kind of normal everyday types of sound. But all of a sudden, right at 8:46:26 Eastern Daylight Time, you see a big click, a pulse of a kind of a high spike type of vibration in there. And that's the record of the first impact, the plane that hit that tower. Okay? And as we move along then, along the line to the right, we see another one. And this is where the second tower got hit. Now as time passes, the black line and then the red line, we're coming down on that third line right here at 9:59:04, you see a really large spike, way up and down, practically goes off the screen, off the chart. Time passes some more. All of a sudden we get another great big spike on the last black line. Well, these much larger vibrational records here are when the buildings collapsed. I think the sad part about this, when I think about it in 9/11, is just to think of the people who were dying at these moments. And this is a record of what happened. This is simply vibration, but it also is a story about something that happened at a particular time in our history, and it really has changed things. But I might ask you, well, why is the impact spike so much smaller than the collapse spike? When you think about it. Well, think about when the impact took place hundreds of feet, many, many floors above the street, and the plane hit the building. That vibration has to come all the way down, be dissipated through the structure of the building, to go along the street, and then move out to the seismograph station. Whereas all of the mass of the building, when it came crashing down and collapsing, all of that weight, when it hit the ground, was much more force. That's why it made a much larger peak on that particular seismogram. All right, let's take a look at the body types now, or the wave types, okay? Now, inside the Earth, when the rock fractures, I said that the energy is given off, correct? That you have energy goes and moves away from that hypocenter in spherical wave fronts, in continuous spherical wave fronts away from that point. And since those wave fronts are moving through the body of the Earth, okay, we call that kind of motion a body wave. And there's two main kinds of body waves, and we're trying to show these schematically in the diagram here in the text, as we see up here. They're using kind of a slinky or a spring to show a push-pull kind of contraction, expansion of the energy moving through a material with these springs, a P wave. So the vibration of the ground, the vibrational style of a P wave is that the vibration is going to be parallel to the direction that arrow is moving. So if the energy is moving from left to right, and if you look up here as I move the cursor, okay, watch what happens. Here's the cursor vibrating parallel to the direction, but it vibrates along that way. Okay, so the vibration is parallel to the direction it moves. That's one kind of wave. The one on the bottom of the screen, the second body wave, the secondary wave, is also called a shear wave. A shear wave, and they're trying to show if you kind of snap a rope and let a little sine wave pattern move through the rope and advance, from this case from left to right, the vibrational pattern of an S wave is not parallel to the direction it moves, it's perpendicular, up and down. So watch this with the cursor again. If I'm moving the cursor up and down, as I move from left to right, it's going to make a pattern of a sine wave. Thus, they're trying to show that with the rope. So it has to travel a greater distance to move. So since it's traveling a greater distance, in fact, it's about 1.7 times longer, almost 2 times the distance to go there, it's got to travel a greater distance. The velocity is the same. That's why they're secondary. That's why they get there second. So when the ground breaks, these two kind of vibrations leave that hypocenter and migrate out in spherical wavefronts through the Earth. Now eventually that spherical wavefront is going to make it to the surface of the Earth, between the air and the solid part of the Earth, the body of the Earth. When that happens, when these P and S waves hit that interface, they generate and new waveforms are created. And they're called surface waves. Now in this sketch up here, I'm going to give you the names of these two. One's called a Rayleigh wave, Rayleigh, and the second one is called a Love wave. Now let's take a look at the first schematic down here on the bottom. I've got several of these to show you. This one's from your text. Is that nickname for a Rayleigh wave is ground roll. Notice in this picture they got, the ground is going up and down and rolling like waves on the ocean, kind of circular up and down motion as the energy moves from left to right. And the amount of movement up and down of the ground can be maybe a few inches to many feet. The bigger the earthquake, the more the earth can go up and down. If you're standing on the ground and you're seeing a Rayleigh wave, that's kind of disturbing to some people. Terra firma is not firma anymore. It's moving up and down like solid rocks doing this, up and down on the ground. So Rayleigh wave is a kind of ground roll, up and down motion of the ground type of vibration. But it's a much bigger wavelength. The bigger that is, obviously it's going to destroy something. The second wave, though, a love wave, is a sideways kind of motion. And in your text they have a schematic that looks like this, where they're using the top of the ocean to move across from left to right. But they ask you, when you look at this in the book, to view it as if you're saying, I'm looking down on the surface of the earth. I'm looking down, and so instead of being up and down motion like it kind of implies, kind of misrepresents, it's really a sideways motion. So Rayleigh waves are up and down. Love waves are sideways shaking motion. They're kind of like a shear wave, but much bigger amplitude. Let's look at another. Well, over here on the right-hand side, I kind of show you a picture of a building that's built on these kind of struts or pedestals. When you have sideways motion, and that sideways motion can very easily shear off structures at their base. So of all of the types of waves that cause damage to buildings, P and S waves don't cause any damage. They don't cause any damage at all. Rayleigh waves, up and down motion, can cause a little damage, but the most dominant damage to buildings and structures are love waves because of that sideways shearing motion that takes place. Here's another kind of color drawing of on the top a love wave showing that sideways motion. Here they have a highway cutting across it. So that is really a damaging type of force, whereas the one on the bottom is kind of a rolly up and down. Both cause damage. They're surface waves. They move along the surface of the earth where we live. So remember that. Love is the worst. Love is great, but love waves are bad. Well, let's see here. Let's move on to go back one. That's all right. All right. Now, one of the things geologists use to measure something else and determine something else about hypocenters and epicenters of earthquakes is we look at and we plot on a graph how far away a particular signal is picked up. We plot this on a graph. So let's take a look at our thing. We've got on the vertical column, we have minutes after the start of the earthquake. On the vertical column, 5, 10, 15, 20 minutes after the earthquake occurred. And on the horizontal scale, we have distance. Now we know that the lowest curve on here is the P wave because they'll go the fastest. So that's why you're going to arrive the quickest on those. S waves are second, and surface waves like this love wave, much slower, will be third. So what we do is we're able to create a lag time graph like this. This is called a lag time graph. And what we measure and utilize from it is a time value between when the P wave arrives and when the S wave arrives. We get that off the seismogram. Remember, the seismograms had lines on them. Those lines were in seconds or minutes of time as that drum slowly goes around the cylinder on the seismograph. So it's that lag time that we can use, and then we say, okay, if sound can be transmitted at 10,000 feet per second or 15,000 feet per second, and I can figure out how to, figure out what kind of rocket's going through from that velocity, then and I've got this lag time value, I can say, all right, at my seismograph station, I know it took so many, it traveled so many miles to get to that particular seismograph station. But from which direction did it come from? Say we had a seismograph station here at Hays, Kansas, at the university. And you go out there and you're watching the seismogram and you see the needle start to go up. You say, well, there's been an earthquake somewhere. Since the energy goes out in spherical wave fronts, it could have come from east, north, south, west, any direction. We don't know from which direction it came from. So how do we locate that epicenter? How do we pinpoint it? Well, what we have to do is have to have a minimum of 3 seismic stations. That's called triangulation. So let's take a look at this map on the right-hand side here. The method used to locate the epicenter is called triangulation. So in Columbus, at the seismograph station, they took out the seismogram. They said, okay, there's so much time between the arrival of the P wave and the S wave. I go to that lag time chart. I slide a line down until I match up the time between the two curves, and I go straight to the bottom of the graph and I pick out the distance. But it could have come from any direction. So I say, well, say it's 2,000 miles away or 1,000 miles away. Then I have to draw a circle around Columbus that's 1,000 miles. Now, that's really not 1,000 miles from Columbus to St. Louis, but we'll say it is for all general purposes. All right. Now, there's a second earthquake station in St. Louis. The lag time between the arrival and the P and S is shorter, so it's not too far. We draw another circle around St. Louis. Well, there's another one down in Memphis. Okay. Now, what do 2 circles that intersect have in common? A point up here, north of St. Louis, one further down by New Madrid. So it's one of these 2 points. So we need a third station. In the case there's one in Memphis, lag time was even less. A third circle where all 3 circles mutually intersect. That's the epicenter. That's how they get those dots on the map. Now, if you want to know how far below the surface it is, because these are circles, right? It's 2-dimensional. 3-dimensional are spheres. So we simply use spherical trigonometry techniques to see where 3 spheres intersect, and that's the position of the hypocenter, the actual break in the ground. So remember that triangulation is a method of how we detect and put the epicenter on a map. You have to have 3 seismic stations. Now, natural earthquakes are the main things we've been talking about here. But what's the difference on a seismogram between a natural earthquake vibration and an explosion of some sort? In the Cold War, particularly between, of course, Russia, the Soviet Union, previous Soviet Union, and the United States, was when we were detonating our bombs. And we didn't want anybody to know about it, so if you're on a particular part of the earth where they can't be detected, you would want to hide it. Now, eventually, we had enough seismograph stations all over the whole world that you couldn't hide a vibration anywhere. Each side would have their own allies and strategically positioned types of more and better seismograph stations. Geologists benefited from that kind of Cold War, technology. So what does it look like on a sheet? Here we've got some nuclear bombs that were being tested. Here's the one down in, we remember the soldiers and some of the things with that happened. All right. Well, what about mine blast? Here's an open pit mine, big quarry out in Colorado. There's an explosion. In fact, in this picture, you can actually see some of the dots where they drilled holes and put the charges in the ground. And eventually, this whole thing would explode and rumple up and blast in little pieces, and they come in and truck it out and then process the ore. So what about a mine blast? Let's see if this works. I want to see if I can make this particular link. It doesn't seem to want to do it. I guess right now maybe the internet connection is not working, but let's see. How can I get back here? Doesn't seem to want to work on that. And there's a site that I could go to at Southern Methodist University where you could get online and watch explosions of different types, where they would set up a sensor device to pick up on vibration signals, and they would take a movie, a video of the explosion, and then going, as the explosion occurs in the image that you see, across the screen are those wavelengths, and they show you the progress of where the spikes come into play and the arrival of the different waves, because they're trying to figure out, what does this stuff look like? You know, in Golden, Colorado, they say, well, is this a natural earthquake, or is that somebody detonating, you know, TNT out in a coal mine in Price, Utah? Well, they know it. They can recognize the signatures. They know what these things look like. Let's see if I can, again, back off of that, since that's not going to work, and we'll move on. Here's the photograph in the top left-hand picture of what this looks like at this website. This is a still. I can't make it go. But the actual, when you get to it, make it work, you'll see the ground real still, and then the explosion-style hearts. And this red line would migrate through, and you could see the type of patterns. And they're analyzing the physics of this, the frequencies and the bandwidth and so on. But there's all kinds of sound. Here we have traffic of what is the noise traffic background that might be on seismograms for cars. Here's trains. This happens to be something that wouldn't be picked up maybe on a seismogram per se, but this is the shuttle explosion when it re-entered the Earth. They picked up on, they had things pointed into the sky at this time, because often there's a sonic boom when this thing hits a certain part of the atmosphere you can pick up on. So we're analyzing a lot. You know, all these different explosions, from highway construction to mines, okay? They're everywhere. And they're part of the process. And how do we delineate between a natural earthquake and an explosion of some sort? Well, the ones we just looked at, there's a category. I want to give you a new word again to your vocabulary. Anthropogenic. That means human-induced. Things that people do. Anthropogenic types of earthquakes, so to speak. Now, next lecture, towards the end of next lecture, we're going to look at a few more examples and types of anthropogenic earthquakes and faulting that takes place and reasons why. But I've got two seismograms up here, and there's a real, not simple, but close-like kind of pattern that develops when you look at the seismograms between a natural quake and an explosion of some sort that helped us in the Cold War to catch people in lies and so on. The top one is a natural. You get your P wave arrivals, then your S waves, then the long surface waves. You get a real distinct kind of spread out separation of these. Whereas with explosions in particular, you tend to get a real quick high spike, and it seems to tail off a little bit. You don't get quite the P, S, L, different types of breakdowns of your surface waves. So for you to remember for a test question, if I throw this at you on the test, what's the difference between the two? Explosions. Anthropogenic type seismograms tend to have a more spiked first arrival. In other words, a higher peak. So if you remember that phraseology, a more spiked type, you'll do just fine on remembering the difference between the two. So we've seen these seismograms. We're getting a little feel about what they are, the wave patterns that develop in them. But 100 years ago, 200 years ago, we didn't have seismograph stations. All we had was people watching things, visual. One of the types of scales that evolved was the Mercalli scale. And it's simply a visual or descriptive explanation of what happened during that particular quake. And it's on a Roman numeral scale of 1 to 12. 1, and I'll read it to you, but you can find the Mercalli scale in your book. It says it's not felt except by a very few people under especially favorable circumstances. Well, that's pretty kind of loosely stated in a way. And you get to the very last one on 12. It says damage nearly total. Ground surfaces seem to move in waves. Lines of sight and level are distorted. Objects are thrown up in the air, probably maybe even you. All right? So simply a descriptive of how much damage or what kind of goes on. And that's all we had for a long, long time. But after that, we got a little more technical. And so this next slide here has to do with measuring the force of earthquakes. And we're going to look at this several ways, 2 ways. One of these magnitude scales that measures the force is where we measure the energy that is released. The energy that is released. And I want you to see that the word released is underlined, as opposed to another kind of magnitude type of scale called the Richter scale. Has to do with the energy that is received. So we talk about energy released. That's what's going on right at the actual fault rupture surface, the hypocenter. And you could describe that in terms of physics, in terms of energy, like an erg. Erg would be a unit of force. All right, now we won't go into that in here, but that's the energy that's released. Whereas the seismograph stations with the little needles that move up and down or sideways and record that little wiggly seismogram, that's measuring simply energy being received by an instrument. And a gentleman named Richter was the one who began to really analyze these and calculate what they were. So I'm going to say a couple things about the differences between the 2 scales down at the bottom of the screen. But first I'd like to mention that business in the middle. The largest quake ever recorded right now has been about 8.9. Now rocks are not strong enough to be any higher than that. Now 8.9 is on the Richter scale. On the energy scale, you notice the number's different. It's 9.5. Now in the media, when you hear CNN or a local television station or a radio station or a newspaper record a number like 7.5 or 6.2 or 3.1, the number they're giving you all the time is the Richter scale. It's very easily and more quickly evaluated. It's that Richter scale number that gets reported. Now when we actually try to measure the energy, it's not just something off a seismogram, it's how big is the rupture surface? What kind of rock is involved? What are the elastic parameters of that rock? So it's a lot more technical. And when they evaluate that energy, it's usually a higher number. Now rocks cannot usually get any higher than 8.9 on the Richter scale because rocks aren't strong enough. Remember what the earthquake is? Rocks are under stress, right? And rocks have a certain amount of strength. Well, the rocks that are on this planet that are involved near the surface of the earth aren't any stronger than that. They can only get that high and boom, that's the energy you can give off from it. That's it. Now let's take a little closer look at the 2 scales, both energy versus the one received. R stands for Richter. Got a capital R for Richter up here. Both of these scales are logarithmic. They're logarithmic scales. So if I reported to you in the news that, oh, there was an earthquake of a 2. There was an earthquake of a 2 on the Richter scale. And the next day there was an earthquake of a 3 on the earthquake scale. All that means is that on a Richter scale value, a 3 is 10 times greater than a 2. So if you go from a 2 to a 4, what's the difference? It would be 10 times 10. So a 4 is 100 times greater than a 2. Sometimes you hear the news say, well, they reevaluated this in California and they changed it from a 5.6 to a 5.9. And you go, well, big deal. Well, when they're talking about this energy received or vibration, the difference between even a decimal point on a logarithmic scale is big. But what really counts is the magnitude, the actual energy given off. Take a look at M at the bottom. It's an increase of 1 unit. So if I went from a 2 to a 3, the amount of energy is 30 times greater. That the buildings are experiencing that energy vibration. It's the seismograph's needle that's moving up and down for the Richter scale, the buildings, and we feel the real energy. So what's the difference between a 4 and a 2 on the energy scale? 30 times 30, which is what? 900 times more. So all of a sudden, when you see them in the news talk about the difference between a 4 and a 6, or a 4 and a 7, energy-wise, and the effect on human life and structures, it's very, very big. Now, where does Richter scale get that number that they report to you in the news? Well, they look at a seismogram, they get out a little measuring tool, and they measure the amplitude of the P wave, or excuse me, the first arrival of that, the P wave, excuse me, and measured in units of microns. And they represent it in scientific notation. So look at this. It says 10 to the fourth. That's 1 times 10 to the fourth. Well, that's an exponent in scientific notation, okay? So what you are given, this would be an example of a 4 on the Richter scale. You're given the exponent number. So 10 to the fourth is what? 10 times 10 times 10 times 10 microns. It's the height of the line. That's all it is. So depending upon the type of seismograph you got, it can vary. So that's where that little number comes from that you hear in the news for the Richter scale. It's what's received, what the vibration is picked up by the seismograph itself. I throw this table at you just because of the idea of, the bigger the quake is, obviously, the more energy that's being released. But often associated with big earthquakes is that the ground tends to vibrate longer, too. So imagine the ground roll being really big, and then having a little bit of component of love waves, sideways motion thrown in, and you're trying to walk around the ground being twisted all around, and then it keeps going, and it keeps going. 30 to 90 seconds sounds, that's not very long. That's a very long time to experience that, of terra firma actually moving around like that. And it does extreme damage to buildings when it happens. So hopefully we don't have as many big ones because the duration is usually longer in that vibration. Well, geologists also take advantage of these seismograms in calculating velocity, of how fast the sound is traveling through different kinds of rock types in the earth. Okay? It gives us clues to the interior of the earth when we evaluate these velocities. On the right-hand side of the diagram is a kind of a velocity scale of increasing depth. As you go from left to right, the velocity, how fast the sound travels through something, this would be 14,000 kilometers per second on the far right to 4 on the left. And if you record that in a vertical scale for depth going from the outside of the thin lithosphere of the earth and down into the core, you can see that the velocities change. It's part of that seismic tomography stuff we looked at in the previous lecture, of being able to take these velocities and 3D model it to different zones of high velocity, low velocity, warm, cold spots in the interior of the earth. So we begin to conjure up names for these parts: lithosphere, asthenosphere, mantle, outer core, inner core. So that's where we came up with this stuff. We learned about the interior of the earth mainly through seismology. All right, let's take a look at this other thing I mentioned early on in the lecture today about when the rocks break and fracture and there's movement and there's offset, that's referred to as a fault. And this plane, this fracture that's inside of the earth is a fault. Well, sometimes the movement styles are going to be different. There's going to be different types of faults, and we're going to look at just a few of them in here, just some of the generic ones. So I use this figure from your book to kind of talk about the terminology you have to deal with before you can define some of the types. And this terminology actually came from mines. We know that a lot of ore deposits are associated with fault zones, where rocks are crushed along the fault. Waters with minerals dissolved in them percolate through those fractures and the rubble along the fault zone and precipitate out economic deposits. So the miners go following the ore deposits down underground. So here in the cartoon you've got these guys hiking down and they're walking on the surface here. Their feet are on this side, on this block. So the stuff to the left and down here is that anywhere below that line where their feet were, that's referred to as the footwall, because their feet were on it. It's real simple. It's a mining term. Whereas the rocks over here on the top of that adit, that kind of going down into the mine, it's hanging above their head. So they simply call it the hanging wall. Again, it's a mining term. But what we're going to do then, because we've defined the rock zone above the fault and below the fault, we're going to say, well, which one went up and which one went down, or which one didn't go anywhere? So we use three simple faults here that you need to remember. Now in this particular picture, see this wavy line along the top, this layer of rock? It's offset. If you were to go straight across, it's been offset. So this has done what? It's moved up. The same with this layer and the other one you can't see further down, but they've been offset. And so which block, which side moved which way relative to the other? Well, the hanging wall moved up relative to the foot wall. So we use that to define some types of faults. Now in the case of this one here, we have the fault. This block on this side, above it is what? The hanging wall. Anywhere below it over here to the left is the foot wall. So what happened here? Which way did the hanging wall move down? Well, we show with arrows the hanging wall did what? It dropped down. So we define something where that happens as a normal fault. And it's where the rocks are being pulled apart by tensional forces, divergent type of conditions. All right? So what do you need to remember about fault types and stuff for the test or quizzes here? That in the case of normal faulting, the hanging wall has dropped down. Now, if it's just the opposite, where the hanging wall moves up, like in the beginning picture with the miners in it, here they're missing in this picture. The hanging wall on the right-hand side, this is the hanging wall, it's above the fault, has moved upward, and again we show these arrows. You form that by compression, convergent plate boundaries. The rock's fractured, energy's given off, but the hanging wall moved up. We've got two names in our vocabulary for this kind of movement where the hanging wall goes up. It's called reverse or thrust. The general difference has to do with how steeply dipping or inclined is the fault plane. If it's really, really a low angle, it's called thrust. If it's real steep, it's called a reverse, but we don't need to go into that in here. So remember that reverse or thrust faults, the hanging wall does what? Moves up. And the third and the last one, I'll use this cartoon to express it. This individual here in the cartoon is standing on the surface of the earth. And he's kind of straddling the fault. Got 1 foot on one side, 1 foot on the other. And if you follow that fault trace between the feet and come to the edge, say this was the edge of a quarry, went straight down in the earth, the fault planes of this type are nearly vertical. Okay? They're nearly vertical in this case. And so this style where they're moving sideways, kind of like our third type of plate boundary, transform boundary, this name we give to this type of fault is called a strike slip. It's slipping along a direction. The alignment or direction of this line in geology, we can talk about it in terms of compass directions. We call that strike. But the slippage is sideways, like the San Andreas Fault in California. And the faults are usually vertical, but when you look in the cross-section, down here in the green, there is no up or down movement. There is no up and down movement in a strike-slip fault. There is no hanging wall or foot wall because the fault's vertical. They refer to this fault as a right lateral fault. I'll give you a real simple idea. If you're standing here on this side of the fault where the cursor is, everybody look at that right now, look at the slide. As you're right by the cursor, and if you look at the fault, okay, look across here, and once you get to the fault, which way do you have to turn to find the rock that might have been offset? Well, once you get here, you have to go to the right. That's called a right-handed or right lateral, lateral meaning to the side. If you're standing on this side, where the cursor is, you move to the fault, which way do I have to go to find it? I still got to move to my right. It's left in the picture, but when you're standing there and moving towards it, so you've got to be real careful about which way you're talking about looking, the direction of view when you describe some of these. But the other two should be pretty easy to remember, the normal fault and the reverse thrust fault styles. All right, so kind of a general background of some of that. Let's take a look at some more environmental hazard type of thing, damage to property and life. What can happen? How can you be hurt? How can things be destroyed in an earthquake? And again, in the news, you're hearing about earthquakes all the time. Another one in the Middle East. These countries are just, kind of damaging to everything. Ground movement. Well, the ground, those love waves in particular, the other waves can destroy buildings. If gas lines are broken and catch on fire, or things in the house can catch on fire, you can be burned. Or if you're near a fire and trapped and that fire consumes the oxygen, you will suffocate in that case. And we'll look at some of that examples of what happened in San Francisco in the early 1900s with that. But it still can happen today. Now here's a strange one of these oddities I mentioned in the beginning, a tsunami. Tsunamis are large waves, large sea. We'll look at some of these large waves generated by that. So tsunamis. Or you can rattle the ground enough to cause the side of a mountain to come down or a hill and cause a rock slide or a landslide. And if it hits your house or hits you or your car, you have problems with that. It's damaging. Sometimes you can vibrate the ground so well that if it's liquefied, or if it's got water in it and you vibrate this wetted ground, it'll actually turn it to kind of like a liquid. You've heard of quicksand or quick clay. All right? That's what happens. The ground that's unconsolidated can convert to a liquid. And we'll look at some pictures of this. The process is called liquefaction. If a reservoir dam fails or is broken by the faulting and the earthquake, that water will cascade downhill and, of course, can flood an area. So here's some examples. If you take a look at this little picture in the bottom right-hand corner, watch it shake. This is liquefied sand. And they're vibrating this thing, and watch what happens to the buildings. It just sinks. The building didn't break. It didn't get crushed. Nothing broke in it. But the ground underneath it, the terra firma, we built it on a bad place. And a lot of times we fill in bays and we want to add real estate, and the ground isn't good. And if it's an earthquake-prone region, you're going to have liquefaction take place, like in this area here. And you can see these buildings just fell over. They weren't sheared off and crushed and crumbled. The whole thing just tipped over. In some cases, they'll simply sink into the ground. There was an example in Japan where the bottom 2 or 3 floors just sank downward. The people in those floors were trapped. They drowned. The building didn't get destroyed, per se. It just subsided and went straight into the ground because of liquefaction. Here's some bridge supports underwent it with the material when they built on that particular river. They didn't do it right. So it's an engineering kind of thing that can happen. Here's some pictures in California when the ground can liquefy and squirt out and ooze out of the ground. The goofy nickname for these are called sand boils. I don't particularly like that term, but here you can see the sand had squeezed out, it got liquefied and just injected out of the ground. It was under high pressure. So whether it's a fire, here we are in California again, with the interstate fracturing in the lower left, to gas mains, plus all the water. You got water and gas in the same spot on that one. Look at this rebar, this steel rebar that's supposed to really support and strengthen things. It's like a pretzel. Here we have an earthen dam, or a cement part of the dam with earthen below it. It almost went. The water got here, and they were probably trying to pump it out fast to prevent it, but it didn't break through and didn't go downhill. Otherwise, the whole reservoir would have gone, caused a flood. So numerous examples of that. So how do we try to protect it? Well, this is the job of the engineers. You experiment with different shapes, different structural styles to try to do that. Here, the building over here, you can see these kind of slashing diagonal structures. That's to add additional support to that particular building. So engineering styles of structures, like you can see here from this figure in your textbook. How do you put the pieces of the wood, the steel, the concrete together? We learned kind of a lesson in 9/11. It wasn't so much the vibration as it was the heat that caused things to fail and melt in that. So it's a challenge. If you're going to live in California, you become an engineer involved in housing and structures of high-rises or condominiums or whatever it may be, highways, mines. What's the best way, the strongest thing to put together? Sometimes we try to put them on great big shocks, like in your car, a rubber shock absorber type thing. Sometimes they'll have things that slide sideways, back and forth on the motion. Here's a shot of the Alaskan pipeline. They were always very, very worried about it with an earthquake in Alaska to actually rupture and fracture and leak gas all over the place. Well, they're pumping hot oil through that pipe, which is insulated. They insulate it, and they do all kinds of things. These little towers I'm pointing to here with the yellow arrow, they're like fins on your motorcycle to dissipate heat. because there's hot oil going through that pipe. You don't want the heat through conduction moving out, melting the permanently frozen ground. Then the support structure would collapse. Underneath it, they've got rubber shocks built up underneath there for support. And this central bar that I'm pointing to with the cursor now, across here, if there's an earthquake and this whole ground vibrates back and forth, this thing slides back and forth sideways. So all kinds of things we can do to try to prevent damage to structures. You know, up and down motion, sideways motion, and so on, to see what we can do. Now, once in a while, earthquakes trigger landslides along huge lakes. Here's an example of an old recorded landslide, a collapse of one of the margins of Lake Tahoe. On this western edge of the lake, you can see the old collapse zone and this radar image of the debris field on the bottom, all the large chunks that slid down in there. When that broke loose, it set forth a huge wave. And that wave slid across and hit the east side of the lake. Now, in landlocked areas like this, or large coastal bays, I'll show you another one, the large wave we refer to with a different term, a seiche. S-E-I-C-H-E. A seiche is kind of like a tsunami. A tsunami is one of these large sea waves we'll look at in just a bit. But in the case of Lake Tahoe, it was caused by a landslide. A very large wave blew across the lake, slides up on the shoreline. If there's homes over there, it's going to get damaged. And periodically, that can happen in an earthquake-prone region. You know, one kind of vibration can trigger another thing, and here in this case, it's a landslide. If we look at this one, here's a really cool series of pictures that came from a satellite. An actual record of a large wave on the ocean called a tsunami, all right, a seismic sea wave that was set off on the coast of South America. There was a displacement of the seafloor along the coastline there, and this big ripple wave began to progress across the Pacific Ocean. Here we can see the island of Hawaii, and watch this as it advances. Whoops, wrong way. Let's try again. There we go. There's the beginning. Moves on, starting to approach Hawaii. It's hitting New Zealand already. Watch what happens when it hits Hawaii. Notice these other concentric rings? What's that? That's energy bouncing back off the island. Kind of a secondary wave that's pulsing. And it keeps building and building. And so these things move fast, hundreds of miles an hour. You could be in a boat out at sea, you wouldn't even know it went over you. You thought it was just a big wave. But when that mass of water is pushed across the ocean and it begins to bunch up on the coastlines of the islands or the mainlands and funnels into the continental shelf, the water level rises very quickly. And sometimes you get this huge wave that will come in 10 feet, 50 feet, 100 feet. There's many examples in the geologic history where sometimes these could be big as thousands of feet tall. Meteorite impact, we'll see later on, can cause waves that big and have in our geologic past. And it finally makes it across. So a tsunami. So a lot of the Pacific islands out there have concerns about this. Here's that interesting picture I showed you in the very beginning of the class today. And unfortunately, it was on April Fool's Day, April 1st, 1946. And here's this big tsunami coming into the east part of the big island of Hawaii, in Hilo. And here's the pier being just ripped apart and buildings being destroyed. And this gentleman, who was kind of hanging on for dear life, didn't make it. But people get interested in going down to the coast. Here comes this tsunami. Let's go look at it. And you've seen it on television once in a while, and then all of a sudden the wave goes, oh, it's bigger than I thought. And they run like crazy, and once in a while they get caught up and flushed off the deck or the beach or the boat, and they get killed. But if you're not aware of it, in Hilo, here's right before the wave hits. See the nice calm beach in here, fairly calm, the trees out here, the little peninsula. Well, here it is when the wave comes in now. There's that beginning of that front. Here's all the onlookers going, uh-oh, I made a mistake. The wave's bigger than I thought, and they're booking it. They're running to get away, because there's the wave coming down here, about 40 feet high, coming right downtown in Hilo. And of course, the damage back then in 46 was pretty dramatic. Boats up against buildings, and people killed, people drowned. So we are much, much better in our hazards analysis of tsunamis. We have this early warning system. Spread out all across the ocean basins in the world are these buoys that are set up. They're set up to send a signal to a radio to pick up by a computer system, an early warning system, so to speak. It's called a tsunami early warning system. A little bit on your etymology of words, by the way, if you know what tsunami means. It's from Japanese. Su means harbor. Nami means wave. Okay? Our fancier word for them are seismic sea waves because they're kind of related to kind of displacement of the seafloor, earthquake related. Don't use the word tidal wave. Tides are movement of the ocean surface by gravitational pull of the moon or the sun, mainly. All right? Like the movie, the tidal wave that hit in Poseidon Adventure. It's not a tidal wave, it was one of these to be, I guess, semantically correct. So all around the coast of Hawaii, you can see that they really, they map things out. They want to know what's going on, keep people informed, warning systems. Here's one up in the middle of nowhere in Alaska. You may have seen this on television one day. Had some fishermen out in the bay, just enjoying a nice day out here in the bay, somewhere offshore. And back up here, where the cursor is, the back of this inlet bay, very confined little bay called Lituya Bay. Part of the mountainside gave way. Vibration was too much, it was oversteepened, it was weak, and wham, a huge amount of rock comes sliding down to that bay, and it shoved a giant wall of water across part of this land here, because there's a little glacier lobe that comes around down in here, tore all the trees off this corner right in there, and sent this wave across the island and right across these guys, and that was the biggest surfing experience they ever had in their life in their boat. They survived. They rode this big wave right out into the ocean. There was another boat that didn't make it. So again, it's kind of a sesh or a tsunami-like giant wave in Lituya Bay in Alaska. Here's kind of a topographic map of the area, and right up in this top right-hand corner is where the landslide occurred. The wave set off and came across here. We get a splash mark. Right in here, just ripped the trees and the soil right off from the wave energy and moved on out into the ocean. Might have even had a little effect on the front end of this glacier right in here, a little lobe coming down into the bay. Hawaii today is an interesting spot about wondering about sides of islands, whether it's Hawaii or the Canary Islands or some of these that are in places of volcanic activity and instability. Could they break loose and slide down in the ocean? Well, radar data has shown us there's been many times when the coastlines of the Hawaiian Islands have given way, huge chunks of real estate have slid right down into the ocean. And so today we're monitoring to say, gee whiz, is the land, the rate picking up? A cliff in Hawaii is called a pali. A cliff means, pali means cliff along the coastline. And so all along the polis of the main island, the big island of Hawaii, they're doing global positioning system studies and analyzing movement of the ground. Because if it does speed up, and a couple of times in the last decade it's shown evidence that because you have lava keep pouring out, piling up, you're overburdening the weight of that coastline, and it slips and starts to slide. Now maybe the energy is released, but if you get too much and it breaks loose, we'll get another great big landslide and the whole chunk will tear right off. Again, another tsunami being generated in this case. All right, so what do geologists and seismologists do to say, well, what about predicting earthquakes? What about being able to tell people one is coming and you've got a week to get out, or 2 weeks, or a day? Obviously, the shorter that time period, the more difficult it is to evacuate a city like Los Angeles or San Francisco. So we've buried all kinds of instruments all around the country and used different type technologies to look at ground movement, to look at ground motion and measure rates of change. Over in the top right-hand picture, they're burying a specialized type of tilt meter underground. Now, a tilt meter is simply a fancy bubble balance, very, very sensitive. That if you get some movement of the ground and it tilts slightly, it'll measure it. If you got hundreds of thousands of these tilt meters all over the place, you simply record how much tilting is going on where, and you map it, and you look for the change. Here's one on the side of a volcano, higher up. A creep meter. Creep meter is where you stretch a wire across the fault. And you stretch that wire across and it's touched on the ground on the opposite side of the fault, so if there's movement, the wire will stretch or shrink, depending upon the movement. So we measure how much stretch is taking place. And again, what you look for is rate of change. If the rate speeds up, you go, uh-oh, we better look at this more closely. One thing Americans didn't do for a long time, but the Chinese did, and some other countries, to look at animal behavior, because sometimes animals, certain animals, seem to sense changes in things. The Chinese would see the panda bears behaving weirdly, or the tigers in the zoos. They looked mainly on zoos and ranches and had it recorded. Well, Californians started doing the same thing. And sure enough, sometimes animal behavior, they get a little, kind of either sad or a little hyper, depending upon what they are. Okay, maybe pace more in their cage. They've been associated with it. So they look at everything, not just that. The word dilatancy has to do with cracks. Lots and lots of fractures in the rock. It's kind of an expansion of volume of the rocks. As the rock begins to slowly crack and split before the fault takes place, if the cracking and splitting speeds up, then you know pretty soon that rock's getting weaker and bam, it's going to break and then the energy will be given off. So it's dilatancy is studying the volume increase of millions of little cracks that develop in the rocks. Kind of just the beginning of the cracking of this big part of the crust. We can go out and study old faults, dig ditches and trenches in them, and look at how often the fault data is recorded in a particular fault surface. Well, this one occurs every 50 years. Well, this one occurs every 500 years. So either we're safe now or one's overdue. Some of the newer technology is taking advantage of satellite data again, using remote sensing with SRI. And SRI is an acronym that stands for Satellite Radar Interferometry. And I think I've got that word spelled out on a slide later on. Satellite Radar Interferometry. And I'll show you a picture of what that is, what that encompasses. And of course, as we said with the coast of Pali, we can use GPS, Global Positioning Systems, to measure movement of the ground, up and down or sideways. So we'll look at some examples of some of these particular features. Here's an example of how we apply GIS. Okay. In this particular area, San Francisco Bay, they're incorporating liquefaction zones to create maps for the public to know if you're going to buy land, I'm not going to buy land there. That's prone to liquefaction. You can't charge me that money, or my insurance rates will be sky high. So wherever you go, see what's available. And GIS is one way of quickly getting the data. Here's a very high-tech, fancy GPS system that will help you, about a $50,000 unit. It helps measure very accurate lateral and vertical movement of the ground. Here's your satellite radar interferometry. There's a satellite in space. It beams a radar signal down to the surface of the Earth, and as the satellite goes around the Earth, it takes a measurement. It comes back around a second time, takes another measurement. What they do is take the two signals of the two paths around the Earth and combine them digitally, and they let the signals interfere with each other. And in doing that, it's able to tell you whether the ground had moved up or down or sideways, and they can color code it. Like here's a fault that was captured by a satellite in California. Here, it looks like little mood rings, doesn't it? The number of colored rings shows how much it has moved. Again, I won't go into the mathematics of this, but here, some of the technology didn't tell us anything. But SRI picked up on subtle ground movement out in Hawaii, that magma was shifting underground, maybe beginning to erupt. Let's see if this will kick in for me. Here's kind of a three-dimensional computer modeling analysis to say, well, let's look at the hypocenters and plot them up. And here we can actually line them up and begin to see that they line up on a planar feature in our diagrams. So there's lots of ways we're trying to utilize this data to predict stuff. I'll throw this one slide here at you. It's kind of interesting. This little seismic rosette. Some art person thought it'd be cool to take some sparkly colored sand, put it in the bottom of a dish, suspend a little kind of pendulum over it, and during an earthquake, let the thing shake underneath there. And this pattern that got moved around in the sand is kind of a specific pattern to that earthquake. Everyone's different. They'll sell them as art. So it's kind of ingenious. They took some science, they put the art together with it, and kind of worked. So before we're done today, I want to remind you one more time that, this is the end of the material for Exam 1, so be prepared for it. Check Blackboard out for the specific times of the exam times of when they're going to be. All right, and check out when they kick in on the timers and what dates they are. And if you have trouble with them, you can email me or call me and find out stuff. Say, I can't get online. We'll see what we can do to help you out with it. So that's it for today. We'll see you.
With an earthquake,